Very good. Okay, well.
Do you hear me well?
Yes, we hear you fine.
Okay, great.
Gunnar, can you hear everything fine? Just to check with you.
Yes, everything is good. So
I'm just gonna do a thing of starting the live screening. Okay, that is running and everything is good. Well, good afternoon, everyone. Starting the live screening. Yep, we've started the live screening. Oh God, I got to turn off the. Okay, that is. Let me stop that. Okay. Yes. So welcome and good afternoon. Welcome to London, where we are holding the second part of Condensed Matter in the City. And we've got two talks for you this afternoon, Francesca Ferlaino and Claudio Sciamon. Let me introduce you first to Francesca. Francesca works in Austria, Innsbruck. She's originally from Naples in Italy. And she has been a professor of physics at the University of Innsbruck, at the Institute for Quantum Optics and Quantum Information since 2014, where she runs a big group. She's got multiple awards, including the Grand Prix de Physique Cécile Debuit-Moret École de Physique de Les Ouches from the French Academy of Sciences, and the Junior BEC Award from 2019, and many others that I will not list at this time. She has been working very actively on ultracold atoms and will tell us today about her work on supersolidity. So Francesca, welcome again, and the floor is now yours.
Okay, thank you very much for this invitation and the nice introduction. So it's a great pleasure for me to be in London, although just in 2 dimensions. And actually 2 dimensions will be one part of my talk. So this is pretty in line with this virtual setting. And yes, it's a great pleasure to be here. And so in the talk of today, as it was mentioned, I will speak about ultracold atoms. So let's say quantum system where you have let's say a bunch of particles together in the gas phase, and they kind of form a very let's say exotic and counterintuitive form of matter, of quantum matter. And I would like to tell you the latest news from my group. So in general, I will try to go step by step because so the topic of supersolidity have been challenging scientists since I would say decades by now. And I think we now understand, at least in our ultra-cold gas setting, which are the key ingredients. And I would like to share with you the generality of these ingredients. So, but just to put everything here a little bit in a context. So this, yeah, so we know that in quantum physics, or let's say in the general field of many-body quantum physics, there is a different system can realize many-body phenomena. So we know so that a very prominent example of what we call quantum fluid, where here the word fluid is more related to the fact that the particles are interacting among each other. So, and a prominent example are, for example, the superconductors or superfluid helium, or even, let's say, light via the polariton system. And the system I'm looking at and I'm studying in the experiment are actually quantum gases. So we have a particle that we need to cool down to, let's say, nanokelvin temperature regime. And in this level of regime, the thermal wavelengths given by the de Broglie wavelengths is actually, let's say, extremely large. And so this gives rise to sort of interference effect and effectively to Bose-Einstein condensation. And so this is the system I would like to present to you. And as you know, I mean, this quantum fluid share many different properties among the others. So you can see quantized vortex in, for example, in superfluid helium. As well, you can observe quantized vortex very similar in their universal properties in quantum gases. And but somehow this type of example which I have chosen today, it's also a little bit to highlight the state of matter. No? So we have this idea of having a solid or a liquid or a gas, and but there are other phases of matter that kind of escape to this type of classification regarding, let's say, the basic properties. And so one of the states which have really intrigued many theorists are what is called the supersolid phase. So now this supersolid, it's difficult to visualize because it's kind of paradoxical in the sense that it's a quantum system in which each atom at the same time, let's say, form a part of a solid, so it shows a crystalline order like a solid, but at the same time it flows as a superfluid without friction. So this idea of being, let's say, localized as a solid, but meanwhile flowing as a superfluid is really difficult to visualize. And our, let's say, way of thinking about this state is going back to the Greek mythology and think about Janus, the god Janus, which is a god that have two characters which are embedded, and you cannot split these two characters. And one is looking at the future and one is looking at the past. And our Janus supersolid is a state which have simultaneously crystalline order and superfluid properties. So when this started to happen, I mean, it kind of date back a few decades by now, with the question whether a solid can also be superfluid. And there have been an intense theoretical debate around this question. And so on the one hand, there were arguments back in the 56 from Penrose and Onsager, for example, in which there is the idea that solid and superfluid follow two different orders. And so these two orders, meaning the localization and the superfluid order, are competing, and so they cannot, let's say, live together in the same state. And on the other hand, close in years from this type of work, which I'm mentioning, there have been a sequence of very important work. The first one being maybe the one from Gross in 1957, in which indeed there was some speculation or some theory related to the fact that it was actually possible to have some Bose-Einstein condensation in quantum crystal. So this question became very relevant, whether some Bose-Einstein condensation could actually exist in a solid. And especially relevant, this question have been in, let's say, in the field of helium and in solid helium. And also there have been a very long experimental search of this type of state. And so one can mention back in 2004, to give you a little bit more of the history of how this topic became more and more relevant. There was a paper from Kim and Chan in solid helium showing, let's say, a deviation of the moment of inertia of, let's say, solid helium, which have been connected to the probable observation of a supersolid phase. However, I mean, this work have left a number of open questions in the community, both in experimental group working on the same system and in theory, in a way that it became clear that the observation was maybe not related to really supersolid properties of the state. And about 8 years later, the same two authors have published a paper in which, I mean, they explain that the original observation were not related to the supersolidity in solid helium. So somehow, from a theory, so back in 2012, the point was that maybe solid helium might be a good candidate to observe supersolidity, so to observe also superfluid property into the system, but somehow the range of parameters where this supersolid state could exist, it's not maybe readily accessible. And so from the theoretical point of view, especially, there have been a kind of a shift of thinking. And so the question that then emerged was rather whether a superfluid can be solid. So let's start from a state which is clearly superfluid, and let's see if some crystalline properties like the spontaneous breaking of translational symmetry could emerge into a superfluid state. And so this kind of shift of point of view have been extremely important for our community. And I can mention and list some of the main, let's say, players from the theory side in developing the theory related to this question. And somehow, what do we need to make that the superfluid also show, let's say, crystalline properties? Well, there are, let's say, a set of properties which I would like to list. And certainly cold atom and in general atomic system offer a very rich possibility in terms of platform. And so in general, to have that superfluid, let's say here I'm depicting the sea as an idea of fluid. And so you see that there are these very ordered phase in which there is, let's say, a clear main wavelength that break, let's say, the translational symmetry. So you need to have this state not to impose an optical lattice or to impose externally, let's say, a crystalline structure, but the system itself should spontaneously develop this type of density wave modulation with a specific wavelength. And so to have a specific wavelength emerging into the system, the first important ingredient that one has to put is to have a state, a many-body quantum system in which particles interact with each other, and that the interaction need to have a momentum dependence. Because this momentum dependence will then be able to translate in a specific wavelength into the system. And so in cold atom platform, there are several possibilities to create this momentum dependent interaction between the atoms. One can use, for example, the dipole-double interaction coming from Rydberg gases, or it can be coming from a magnetic dipolar interaction like the dipolar quantum gases. But it's also possible to somehow engineer momentum dependent interaction by coupling Bose-Einstein condensate with light, or by creating, let's say, a type of spin orbit interaction into the system. And so there are both possibilities to have really the innate interaction that nature gives us in some system, like, for example, Rydberg or dipolar quantum gas, or the possibility to actively engineer and shape a momentum-dependent interaction. But this is a very key properties that one would like to have as a first ingredient for supersolidity. And so, yes?
Can I ask a question which will maybe help our audience get a better grip on what a supersolid is? You mentioned of course, a density wave coexisting with superfluidity. But just having a density wave is not enough to make a solid. A solid is made of several intersecting density waves. So that's my first question to you. Is, for example, a paired density wave, which has been discussed in the case of, for example, the cuprates, is that a supersolid or not?
So what you want to have so the most general definition that one would find is that you would like to have a state that breaks spontaneously to symmetry. One is the gauge invariance. So it means, let's say, superfluidity or macroscopic coherence, and the other one that breaks spontaneously translational invariance. That the ground state of the system, let's say the stationary solution, the ground state of the system has to break this to symmetry.
But the word solid implies a rigidity in all dimensions in which the crystal lives. So that would require more than just translational breaking in one direction. So that's my question to you. Does it have to break translation invariance in all three directions or just one direction?
So in the way we think about this is that it can break translational invariance. So, I mean, you can think about supersolid properties in one direction, and so then the breaking will be in one direction, but actually then even better to have it broken in two directions.
Mm-hmm.
So let's say if you think about the plane is broken in both directions, like let's say the surface of the sea that I'm showing here, now, where the translation symmetry is broken in two directions.
And so a charge density wave from your perspective is already a solid.
So from my perspective, the type of density wave we have is such that you have a crystalline dispersion relation, like the Brillouin zone appear in the dispersion relation of the system.
Okay, thank you.
And this you can see, and we measure also this, that so the Brillouin zone, the band mapping, can appear in one direction if the translational symmetry is just broken in one, or it can appear in two different directions.
Thank you.
Okay, so, and let's say, coming back to this idea of a momentum-dependent interaction. So the one that we are working with dipolar quantum gases is the interaction called a dipole-double interaction. So what is interesting in this type of interaction is that it's long range in 3 dimensions, is long range in the sense that the interaction fall down like 1 over R to the cube. And there is a dependence on some angle, and the angle defines, let's say, the orientation of the dipole, let's say, with respect to each other. So, for example, if you have that, if you consider just 2 dipole and you align them head to tail, so this is tail and this is head, and you align in this way, then the dipole-dipole interaction is globally attractive. And if you now indeed align side by side, like here, so do you see my mouse, I guess?
We do, yes. Yeah.
Yeah, okay, great. So then it will be a repulsive interaction. So somehow the orientation of the dipole, it's also determining the sign of the dipole-dipole interaction. And this is very, very important. And now if you think, and now I'm coming a little bit back to your question of 2-dimension and 3-dimension. So all what we are doing, the gas itself, let's say, is a 3-dimensional gas. Okay, but then is a 3-dimensional gas always, and this is a point to keep in mind for the following. But what you have is that if this 3-dimensional gas is, let's say, living in a sphere, now it's completely symmetric. Imagine you have a gas and your container is a sphere. Okay, so it's complete, it's not an elliptic, but it's completely round. Then you can immediately imagine that the anisotropy globally, when you integrate over the whole sphere, lose a little bit the meaning because you will have a lot of particle in this sphere where you have 10 to the 5 atoms. You will have a lot of particle aligned head to tail and a lot of particle aligned side by side. And then let's say the mean effect would kind of make a vanishing dipole-dipole interaction in a sphere. So you need to have slightly more particle aligned along one axis. So to slightly imbalance this attractive versus repulsive part of the dipole-dipole interaction. So in the to make it more, let's say, formal, in the uniform case, when you do the Fourier transform of the dipole-dipole interaction, there is still a momentum dependence, but rather weak. It's kind of a dependence only through the angle. But when you then don't do the uniform case, but you kind of trap your atom, and you make not a sphere, but maybe an ellipsis, or you can have a pancake. Here it seems that they are 2-dimensional, but they are not 2-dimensional, just didn't picturize very well. So you still 3D, the atom can move everywhere, but they are slightly, let's say, more pancake. So there are slightly more repulsive component of the dipole-dipole interaction. And you can have this either in a pancake, or if you elongate your 3D system. But you have particle in all the 3 directions moving, so the scattering is completely 3D. So when you do this, effective is like if you would integrate the dipole-dipole interaction along a surface which is anisotropic. And because of this, you will have explicitly the dependence on K, not only through the angle, because you make, let's say, some K direction more attractive than the others. And so And this is one of the interactions we have in dipolar gas, so the dipole-double interaction. And this interaction has to be, let's say, summed up with another type of interaction, which is our conventional short-range contact type interaction, which effectively depend only on one parameter. It's kind of totally short-range, is a delta function interaction. But the contact interaction have the meaning of controlling, let's say, an offset in controlling the different phase of matter that can be reached into the system. So now if you have an interaction which is K-dependent, and you look at the, let's say, dispersion relation, meaning the energy, the excitation energy as a function of momentum, epsilon K, of course, this interaction also enter into the dispersion relation. And so you would have here an additional term, so this is kinetic energy, and then you have a term of the interaction, which are many body in the sense that depend on the density, and they explicitly depend on the momentum. And so now you can naively think that there is a competition between an interaction that can be attractive and the kinetic energy, which is always repulsive, and this competition results in a minimum in the dispersion relation at the non-trivial K equals 0. So for a momentum which is rather large, so you have this minimum in the dispersion relation. And this we call, in analogy with helium superfluid, a Roton minimum, just because the dispersion relation is quadratic and it's at K momentum. Now the K momentum, which is the momentum of the Roton excitation, is not a specific value given by the Hamiltonian, okay? So it's emerging from the competition of different attractive and repulsive interaction. Now you can play around with, let's say, how deep is this Roton minimum, meaning you can play around, you can actually control the gap, which I call delta here, of the Roton gap, just by changing the offset given by the contact interaction. So this is the contact interaction, which allows us to go to this pink line, let's say, where you hardly see a minimum, to really, let's say, dig a minimum into the spectrum, and in principle the spectrum can even completely soften the Roton and touch 0. And so this type of spectrum has been predicted for dipolar gas in 2003 by Santos and co-worker, and for many years was not observed in experiment. And the reason being simple: you need to create in your lab a system in which the dipole interaction is strong enough, and this was not available. And but then by producing, so we were able to use highly magnetic atom like erbium, dysprosium, so new type of atomic species which have very large magnetic moment, actually are the most magnetic of the whole periodic table. And with these quantum gases of erbium and dysprosium, is actually possible to really observe the Roton. And this is what we observed by doing a spectroscopy of the dispersion relation, and you see that for a given set of parameters there is this minimum appearing. And so now so we know that we need the momentum dependent interaction. We know that the dispersion relation or excitation spectrum show this kind of Roton minimum. And then the final point is that by controlling the scattering length, it's possible to completely soften. Now, this is a very interesting point, because you see this is the spectrum of excitation, but it costs no energy to create Roton excitation into the system because the gap is 0. So in principle, once we enter in a parameter regime like this one, the system should develop spontaneously a lot of Roton excitation. What does it mean really? So it means, one second, where I have it. So it means that there will be some population, not only at K equals 0, which is the ground state, but also some population of the system at K rot. And this you can really see by mapping the momentum distribution. So you see the central peak, these are our atom at K equals 0, and then two side peak, because momentum is conserved, a plus the Roton momentum and minus the Roton momentum. And this is what have been observed. But now come the tricky part, the one that was not easy to understand, I would say, in the experiment, which is the following. Once you get a point in which there is an excitation of the system which require no energy, this immediately, let's say, convert into instability of the system. So any type of small thermal seed would immediately populate this state, and you will have an exponential increase of the population in this mode, just because of instability. So now this instability would mean that the system is not stable, and it would be, yes.
Ask some clarification. So you have anisotropy because of the directions of the spins of the atoms. Is that the case? Is that so? This is just at one point, or is it on an entire sphere? K wrote.
Is on an entire sphere.
It's on the entire sphere. I see. So
it can be.
Why are we then seeing a single spot in figure C, as opposed to a rim of hot spots?
Okay, so I'm not sure I understand the question. Maybe I try again. So here I'm yes.
I mean, this is a two-dimensional plot of K rho versus energy versus K, but K is just the magnitude of K, no? And therefore it should be over an entire sphere that it goes to zero. Is that the correct interpretation? Okay. So, or is it the one point in momentum space?
Okay, so it depends a little bit on the geometry of the system. Mm-hmm. Because I mean, as I mentioned before, in a sphere, okay, in a complete sphere, if you integrate, the dipolar interaction is zero. No, because it's everywhere. In a sphere, you have many atoms oriented everywhere. So if you look at the two-particle level, you can have attractive or repulsive. But if you sum up on a macroscopic and you integrate over a sphere, it's zero because you have as much attraction than repulsion in terms of orientation. So you need to take your sphere and kind of compress. You can either compress a little bit in this direction, and then you would have that the key roton is actually a radial, and so it's kind of a circle in momentum space. Or you can decide to make it a cigar, but it's not, the atoms are not aligned at 1D. The atom can still move, but just, I mean, there is one confinement direction which is much looser than the other two. So they will, let's say, like to move more in the looser direction than in the other. And so in this case, you will have just one linear K roton. And so it's linear in momentum space, it will be 2 points, plus and minus K roton.
Thanks very much.
So in this specific case, the first observation of the roton that we obtained back in 2009, 19 and 18. So this was for a kind of a cigar. So it was a linear roton. So it's actually just 2 points. Is this explaining?
Yeah, thank you. That does a trick. Thank you.
Okay, great. And so, and now this is the softening. And it was, okay, so here. And it was pointed out actually that if you arrive to this roton instability, so where the gap is zero, if for some reason there is some, let's say, additional stabilization term in your Hamiltonian, then the collapse can be stopped and there is a phase transition into a supersolid state. So you would have a new ground state of the system which have a density modulation and fully phase coherence. And this was pointed out by Shlapnikov and co-worker in 2015. And so you see that in this case, you would have a spectrum of excitation with an additional term which might be for some regimes small, which is also repulsive and let's say have a faster dependence in density than the dipole-dipole interaction and the contact interaction. And this term can act as a stabilization. So the rotons soften and the system, instead of, let's say, collapsing, will then make a phase transition to a completely novel ground state, which is modulated, which have this density modulation on top. The problem back in 2015 is that nobody had really a good idea on how to create this stabilization, additional stabilization mechanism into the system. And then, I mean, from other type of observation, it was actually observed that for dipolar quantum gases, there is indeed this type of stabilization, which have been called quantum fluctuation. Now, this is a bit of, I think, not really appropriate name, but somehow when you do the mean field interaction, and you have the dipolar interaction and the contact interaction, it's just, I mean, let's say in a zero order, you have the mean field interaction. The first correction to the mean field is what is called in the community quantum fluctuation. And so it's kind of the first order correction to the mean field. And this first order correction has a faster dependence on the density than the contact interaction, for example, and it's a repulsive one. So it has been introduced and developed for cold atom by Li-Wan-Yang, and it's also called Li-Wan-Yang correction. And so effectively, it played the role of this additional, let's say, term, repulsive term with fast density, let's say, dependence. And so this was observed in contact interacting gas, but the quantum fluctuation is very small for contact interacting gas. And for dipolar gas, I don't want to enter in the detail. It can be really very significant in determining the system. And so with all these three main ingredients together, those are the things that make that the ground state, instead of being let's say a non-modulated ground state, it's expected to really show this density modulation. Now, just take care that this is the ground state for a real system, the one we can have in the lab. So it's a finite size system, and you can have some of this peak here emerging spontaneously into the system. But this type of density modulation survive in the theory also in the limit, let's say, of infinitely elongated or infinitely, let's say, large system. It's not related to a finite size system. And this is the new ground state of the system, which have also the spectrum of excitation change. And I will not review this, but I mean, as I mentioned, you will see that in this state, the excitation spectrum has two Goldstone mode and two phononic branch, one for the crystal following a Brillouin zone and one for the super.
Francesca, a question from the chat, which I'll read out.
Yeah.
Because, this is from Python How. And he or she asks, don't you always get that higher order term automatically through loop corrections, etc.?
Yes, you always get it, but this higher order have a coefficient in front, and this coefficient is small. Now, if you have the dipole-dipole interaction, since every system tries to minimize the energy, the atoms are always trying, let's say, to align and to increase their density in a way to, let's say, maximize the attraction, because the attraction will minimize the energy. So somehow the coefficient, this quantum fluctuation of first order correction is always present, also in simply contact interacting, but it's very small. The difference here is that the density increased very rapidly because the system tried to increase the density to maximize the attraction along the line.
Okay, thank you.
Okay, and so and this type of and so when we studied the first time the roton excitation. So what we saw is that plotting the population in the roton mode, you see that after, let's say, for a given value of the scattering length, when you have the scattering length such that the gap completely soften, or close, you have first a very fast growth of the population into the rotor mode. But then at some point we observed that back in 2018, that this growth was stopped by something. And then the system undergo a much slower dynamic. Okay, and so back at this point, we just speculated that maybe, so this short wavelength density modulation, which is connected to the rotor softening and the stabilization mechanism, this Li-1-Yang term, could actually allow to enter in this type of new ground state, which is a supersolid phase. But we didn't really study it into detail what happens in this lower dynamics part. And now we know that this lower dynamic is due to the fact that the system at some point, let's say, undergo a phase transition into this new ground state. And indeed, very soon after our first observation, it was calculated in a theory work, which I'm quoting here, that for our parameter, indeed, you will have this supersolid behavior in which the ground state itself changes. And so we, of course, once we observed for the first time this state, we were not the only, so we then did many more, let's say, shaped experiment, and also other two groups, one in Pisa and Stuttgart, got a very similar result than what we observed. And effectively, one would have to probe the phase coherence if you really have that this state have a global phase coherence, and we have to study, let's say, how the density modulation actually emerge in this state. And so in the experiment, we have two observables. So just to explain you, typically we have a gas in an harmonic confinement. And so then the density profile of a gas into an harmonic trap is basically, let's say, an inverted parabola without modulation. When we enter in this supersolid phase, then the system spontaneously, let's say, develop a density modulation in real space. And then if you look at the momentum distribution, you would see what I show you, a central peak plus two side peak related to, let's say, 2 pi divided by the wavelengths of this modulation, which is where the rotor momentum is related to the rotor momentum. And so you have now you have to think about your observable. In cold atom experiment, the mapping of the momentum distribution is rather easy. It's a little bit more difficult to show, to observe what is happening really in threat. So this is now an example of the momentum distribution with the 3 peak magnified experiment once we improved our imaging. And then from this interference pattern that we see, we can do the Fourier transform and extract a phase. And you see that the phase, those are hundreds of shots of experiment, they are all, let's say, very much focused in one point. If you would have non-phase coherence, which we also created a non-phase coherence state, you would see this point spreading 360 degrees in this, let's say, angular plot. And then the other observation that we I mean, that was a bit challenging in the experiment is really to observe the formation of this very kind of, you can see it as a density modulation, but you can also imagine as an overlapping small droplet of gas that spontaneously form this state. And so, of course, we studied then the phase diagram of this state, and by changing the scattering length, it's possible to have a normal unmodulated BC. Then we have this, what I introduced as supersolid phase, where you have this density modulation, but still the atom can move everywhere. They are very much connected everywhere. And so these are indistinguishable particles, or you can even go farther in what it would be called a normal, let's say a more normal crystal, where you have this type of droplet that they don't have any density link in between them. And so, there are a bunch of experiments, both in our group, but also in the group of Pisa and Stuttgart, that the way this supersolid phase, this interesting density pattern was accessed by first producing a BC, which is superfluid, and then by changing the scattering lens such that the roton gets softened and you see the appearance of this state. This is a very simple way to enter in the state. However, it also comes with a lot of density fluctuation because at the phase transition, you can never be completely adiabatic. So there is another way that we actually developed in Innsbruck that it's actually directly starting from a classical gas. So it's a thermal gas following the Boltzmann distribution. And then you remove kinetic energy. Let's say you really cool down the system, decrease the energy. 1 second. And until you go to a specific point of the zero temperature phase diagram. And the system condensed directly in a so-called supersolid state. And so this is also what we did with our system. And this is a very smooth, much smoother transition. And the one question we wanted to ask to ourselves is whether from the thermal gas, which is non-phase coherence, neither break the translational symmetry, whether these two symmetry breaks simultaneously or one of the two are breaking before. And so this is what we do now. I show you how we evaporate. We are reducing kinetic energy in the system, and you see this is really entrapped as a gas of atom. Now we just repeat this movie several times, and you see how let's say the density modulated state appear here. So the trap is always a macroscopic harmonic trap, okay? So this shape is not imprinted by the external potential. And then we could follow, let's say, the evaporation. And so each of these line is one frame in time during the evaporation. And we first have, let's say, a thermal gas. You hardly see anything because the density of the thermal gas is very low. And then when we start to cool down, you see the appearance of kind of some density, some let's say density pattern into the system, and then it appears more prominently. And you see that this survive very long for the typical time scale of cold gas. Let's say this is about one second and more. You see the density modulation existing. And so our question was now to understand which one of these two properties, phase coherence or density modulation, appear first. And here again, from the interference pattern, so the momentum distribution, you can define a quantity which is a simple phasor, is a complex phasor, which has an amplitude and a phase. And now the amplitude of the phasor tells you about the modulation. So if you have modulation into the system, you will have, let's say, an interference pattern of this type, and the phase tells you about the global degree of phase coherence. And then one could, from the phasor, introduce two quantity, one which is the, let's say, modulation strength, which you see is the modulus of the phasor. So that means it's simply this part of rho I, because the modulus means that the exponent get 1, and so here there is no information about the phase, or let's say the mean, the average, and then you put the modulus, and this quantity measure the phase coherence. And so by probing the evolution of these two phases, we would be able to see which one of the two properties appear before. And so when we did this, you can see, for example, if you have a thermal gas, you have, and here it's hundreds of measurements. I don't remember if it's 100 or 200 measurements we did. And so you see that they are very much all into the center of this phasor plot. And there is here neither, let's say, phase coherence because it's spreading in 360 degrees, and also it's almost zero radius. So the radius, it's very small. And then when you go in a state which you have modulation, but you don't have global phase coherence, you will still see the spread, but then the radius of the distribution is larger and give you basically AM. And once you have the global phase coherence and modulation, you would have, let's say, a non-symmetric distribution of the experimental point. And with this, I mean, what we observed in the experiment is it's actually, so this, the black is the modulation and the white is the phase. You see that while the evaporation, so you're removing the kinetic energy into the system, the thermal gas first start to be modulated without having any phase coherence, and then develop phase coherence as well. So somehow it seems from our investigation that the density modulation appear before the phase coherence, and it's now still, I mean, under understanding why there is this behavior. So from thermal you go to what we would call crystal, and from crystal you go to phase coherence, and probably this is due to this regime in which you don't have a condensate, but you have a quasi-condensate. So you have population also of a larger K mode. And so this, in all what I showed you so far have been produced, as I mentioned before, in a kind of cigar trap. So the density modulation, so the translational invariance is broken only in one direction. So you kind of have a chain like this one. And there was a lot of question whether it's possible from this kind of 1D supersolid properties to go to 2D supersolid properties, in which you would break the translational symmetry in two directions. And this is what actually we did it recently. It's, I mean, a recent paper from our group, and we were very much, let's say, inspired by what happens to the Ionic Coulomb crystal, although the physics is different. But the idea, the underlying idea in Ionic Coulomb crystal is that you can have a linear chain of crystal. So now each of these spots is one ion. And so if you now, let's say, relax the transversal confinement, you see that the ions start to, let's say, create a sort of zigzag shape. And so a little bit motivated by this, we changed our system, so the dipole trap, the optical confinement, to be able to control better the transverse confinement. And so we started from doing this 1D supersolid that I show you in a sort of cigar shape, to move more and more into a trap which look like more like a surfboard trap. And then for each trap, we kind of evaporated into the final step. Okay, so there is no dynamical change of the trap. We fix the trap and evaporate into different trap. And then you see here for a cigar elongated in one direction trap, you see this one linear chain, and then you have the Fourier transform or the momentum distribution of these three peaks. And then once we make the trap a bit more, let's say, bigger in the transverse direction, at the beginning, nothing happens really. But then at some point, you see that you start to have this type of crossing of the state at the center. And then if you go more, you start to have really, let's say, almost not one chain, but two chains. Also transversally, you start to have let's say, a modulation, and you see the Fourier transform start to change and change even more. And you have, let's say, this type of things in which you have interference peak in the two direction appearing, and more appearing and more appearing when the system become like this. And of course, this is very nice because you have it also now transversally, but still is a little bit sad that you have only two, let's say, peak in the density, and we would like to have more. And these have required again an important step. But first, we wanted to understand if this state is phase coherent. And so, and here we used the same technique as in the 1D. So we probed the density modulation, so the interference pattern, if it's a coherent interference pattern, is like a laser light that interfere, then this would show you global phase coherence. And we did it also for the 2D case, and you see that each of the gray line is one experimental set. You always have the same coherent interference pattern appearing on top of the other. And if you would have, and we could also prepare incoherent state, and you see that if there is incoherence, no macroscopic phase between the whole part of the system, the pattern would wash out. The average pattern will wash out, while here the black is the average pattern showing it. And so we then probed calculated all the phase diagram of the system, because we wanted to create even more extended supersolid, and which were expected actually to have really more more density modulation in the two direction. And then to do this, we had again to change a little bit our trap. And here you see already a more extended state with global phase coherence. And then very recently, we also created a full isotropic trap, let's say a round trap here to see the modulation. And for our atom number, there is this type of flower pattern that is expected from the theory. Again, we had to change our setup, and this is exactly the same flower pattern that we could observe in the experiment, and confirming also that this is phase coherence by looking at the interference pattern. And so, and with this, I would like to, let's say, thank you for your attention, and present the team. So this is the team that did all the experiment in Supersolid, and in addition, I have a Rydberg experiment in Innsbruck. We have a theory team in Innsbruck, and we have also opening for theory and for the theory and the experimental team. And with this, I would like to thank you. And Pierce is sleeping. Yeah. Hi.
I'm not sleeping. I'm relaxing.
Okay.
So, okay. So there we are then. We are now in the phase where we can turn to questions. So do I have any questions from the chat or from the audience? Or maybe in that case, we can return to some of the points that were raised at the very beginning. You focused, I see you focus mainly on the 1D case here. Do you think things will change if you go to a 2D or a higher dimensional supersolid?
What I showed in the last couple of slides is actually that.
Oh, you begin to get a crystalline structure.
Yes, exactly. Yes. In 2 dimension, and now there is there is global phase coherence here as well. So this is what we actually created into the system. Yeah. And this is very interesting because you might ask yourself, how is the momentum of inertia of this state? Whether you would have quantized vortex, how the quantized vortex would survive and enter into the system. So I think it's a platform that's open to a lot of investigation. Shouldn't you start to see dots at multiple spots that go beyond that point once you start to get more than one cube vector? Sorry, a point that goes beyond what? Sorry, more. So here you have six additional soft modes in your spectrum, what? Yeah, so it's dependent on the geometry of the system and how many atoms you have. Okay, so in the experiment we cannot decide. So I mean, the number of the total atom number is limited. And so if you would go to higher atom number, you would see more spots. More spots, I see. Okay. Yes. It's let's say it's depending here. Here's the number of droplets of point that you call it point that this would be created, no? And you can go from 1, let's say, to, I don't know, for example, 12 or 16 spots. It only depends on the atom number, just that the experiment kind of are around this. So they can hardly go too much higher than this line. Good. Other questions? Oh, yeah, we've got, so I'm not seeing the top of the chat. Okay, good. Okay, John Saunders, would you like to unmute your mic and ask a question?
Thank you. So this is very beautiful work, and thanks very much for the presentation. I guess it's about nomenclature of what one means by a supersolid, and maybe there are different kinds of supersolid. If I understood your talk correctly, and correct me if I'm wrong, what the dipolar interaction and the shape of the trap does is to give rise to a density modulation. So in regions of high density, you have many atoms. In some sense, they're droplets condensed by the dipolar interaction, And then these droplets are coupled together, and so you end up with phase coherence across the entire sample. And if that understanding is correct, then I think it's probably legitimate to refer to that as a supersolid. There's another kind of supersolid which was part of the initial quest in helium, where the density variation is, as it were, on the atomic scale. So you get the peaks in density are on the atom sites, and the solid structure is forming spontaneously, and you have phase coherence across that solid structure. So my question is that distinction and is that understanding correct, or am I misguided?
No, actually, you're not misguided, because in that, so from my understanding, I'm not an expert of solid state, but from my understanding, you have really a crystalline, let's say, structure. And so in each, let's say, corner of your crystal, you have one single atom. And then there are some vacancy. And if the temperature is low enough, this vacancy can move. But by moving, so they can both condense all together. So they lose the single particle nature, but they both condense microscopically. And if one vacancy moves, it has to move also, let's say, the crystalline part. Okay, because the vacancy move, and so one of the filled site should become empty. And so, and this create, let's say the two properties. So the condensation of the vacancy plus the movement of the crystalline structure, and those are connected. Now, so in one side of the crystal, there is exactly one atom, as you said. And so while here we have a system which is different, because in each of our sites that you can call droplet, we have something like 10 to the 4 atoms. Indeed, the droplet itself can be superfluid. Even if they are not connected, each of these, let's say, high density region, the particle which are 10 to the 4 can be superfluid.
Yes,
and that their own, yeah.
So thank you. So since we're maybe dealing with apples and oranges here, then maybe you'll be interested in the paper that we published with the chairman as a co-author on two-dimensional helium, in which we interpreted those results in terms of an intertwined state of two-dimensional density wave order and a phase coherent superfluid. So I don't know if you're familiar with that work, but let me just draw it to your attention. Thank you.
Thank you. No, I will have a look. What I find also somehow interesting of, let's say, this type of system that, let's say, connect with one crystalline properties is how the spectrum of excitation change. And this is the figure I'm showing here. So first of all, the spectrum is discretized because we have a finite size system, of course. And you see that in the first one, the one at 51, this is an unmodulated ground state. So it's an ordinary Bose-Einstein condensate in gas phase. And then here the ground state is still unmodulated, but the Roton excitation start to appear. And then the Roton gap start to close. And once it closes, you can see, let's say, the appearance, you can see a few things. First, the appearance of two branches. So one is this one that you see, like this is periodic, like crystalline branch, okay? And the second one you also see is connected to the superfluid properties. Now, more you go to this state with density modulation and phase coherence into the normal crystal, this second branch, so there is two phonon branch here, the second branch completely flattened down until a point to almost disappear. And so here you have really just a crystal where the superfluid branch disappeared. And now it's a little bit hard to see in this finite size system, but I mean, similar calculation have been done in the in the, let's say, uniform case, and you see this branch much better. Yeah.
So may I follow up? So if you write down an order parameter for this state, have you thought of that, and how does that differ from the order parameter of a solid and the order parameter of a superfluid?
So from what I know at the moment, it's not, let's say, still developed a clear, let's say, I would say, type of Ginzburg-Landau theory for the supersolid in the dipolar gas, where you have one order parameter that determine the global phase transition. Somehow, it is a little bit a question also which type of phase transition is, if it's first order phase transition or second order. And what we are understanding now, that really depending on the parameter of the system, the number of atoms, the size, it can actually be either, let's say, basically a first order or a second order phase transition. There's always finite size system, so the order of the transition is not very well defined. And yes, so, and you have a wave function that you can, of course, you can define a global wave function, which would have the periodicity of this crystalline periodicity. Like if you see here, you have always a wave function that you linearize for the Bogoliubov spectrum, plus the global phase coherence. So you will have the phase and the density determining the order parameter.
Great. Well, now we've got lots of questions, and so let's go down the list. Next question, Andrew Ho.
Okay, can you hear me?
Oh. Yes.
You have to come up.
Okay.
Turn off your mic.
Okay.
Good.
So thank you very much for a very beautiful talk. And you showed some beautiful data about phase coherence in this system here. And I wonder, since it's also a solid, or even though it may not be a conventional solid, what kind of cold atom probes can you use to test for the solid properties? Especially when you have your 2D system, we can start asking interesting questions like, are there shear modes and so on?
Yeah, I mean, this is a good, so this is a good question, and I think there is an answer. Because I mean, there is maybe an answer. So, so what you can think about in cold atom experiment to have similar probe as the one of, let's say, neutron scattering. So you can introduce it, and we have done it, and we have also a paper on that, to put sort of really a high energy probe into the system. And you can see how is, let's say, so you can extract the structure factor of the system. So how the system reacts to a high energy probe, like in neutron scattering. So this, for example, you could do.
But in solid helium-4, for example, people actually can measure shear by having two plates connected to the solid and then literally shearing those plates. Is that something that you can imagine doing, or it's kind of hard?
Let's say the problem is that so this shear modulus, so you could kind of also compress this gas.
Right.
And let's say measure the compressibility. The problem is that when you, so not the problem, but maybe the interesting part is when you compress, you have a mixing of the system, so both the crystalline part, the crystalline moda, which are, for example, so maybe I can go in the next slide, which is more clear. So you have here a crystalline branch of the system, which would be this one. And then you have a superfluid branch that you would see here. Now, if you compress the system, you want to measure the shear modulus or making, let's say, even, let's say, a kind of, let's say, a tension in one direction, you might have a mixing of the superfluid response and the crystal response of the system. So they are not completely disentangled. So each of these modes, we can say that they are dominant superfluid or dominant crystalline by looking at how they move. So for example, the modes which are here on top, they move in a way, let's say that if you see my hand, so it's kind of a rigid, some of the mode, to give you an example, is like this one. And the modes which are below are modes in which the peak density change. So they maybe don't change the distance, but actually this is just is an extreme case. In reality, this type of mode, there is always a little bit of mixing about the density mode, where the density change, and the crystal mode. But yes, we could do another thing which we are now currently working is on the scissor mode. So to measure the moment of inertia of the system, which might be another thing related to what you were. And the third thing is to try to put angular momentum into the system, let's say the vortex. And this is also something which is on the to-do list.
Right. Thank you.
Yeah.
Okay, good. Now, Gunnar, would you like to ask a question?
Yeah, sure. So my question was about sort of different regimes of this supersolid that you might be able to explore, and to which extent the atomic physics gives you access to that here. So I mean, you end up with kind of droplets that have fairly high numbers of atoms currently, and they have some length scale with which they're separated. I mean, is there some Feshbach resonances that could be tuned, or some other interaction parameters that would allow you to kind of change the balance between, you know, the spacing of these droplets and how many atoms they end up having?
Yes, yes, exactly. So if you look at the phase diagram, no time, but if you look at the phase, so if you would look at the phase diagram, and for example, you consider to move horizontally. Mm-hmm. So the atom number do not change if you move horizontally, but you can go from this light blue color, so 10 droplet to 8 droplet to 9 to 8 to 7. So you could kind of moving in this direction, decrease the number of droplet or increase in the other way around. And so it means the atom in each droplet, since the total atom number is constant, is changing. And this you can do by changing the trap aspect ratio. So how deformed he is with respect to a spherical geometry. So more elliptical or less elliptical.
Right,
And,
but I mean, this is kind of just allowing the gas to expand, right? So you would expect that if it expands more into 2D, then it probably forms more droplets. But I mean, my question was maybe about the underlying length scale that of the solid, right? So I mean, is that related in a simple way to, you know, the Fermi momentum or so, or is it
so in the length scale? So in 1D, the lattice spacing is related to the Roton excitation.
Okay.
And the Roton excitation, let's say in some near the minimum, you can extract an analytic formula, and it's depending on the scattering length, although in a smooth way, and it's depending on how much is the ellipticity of your trap, the Roton momentum. So how much you make the attractive gaining, or attractive part of the dipolar interaction gaining over the repulsive part.
Mm-hmm. Yeah, I see. And I guess, I mean, can you get some interesting effects by tilting the magnetic field, maybe to get different, or electric field?
Yes.
To get different alignment of the dipole?
Yes, I think this is very interesting. By tilting the magnetic field effectively, so since the dipolar gas is very soft, in the sense is not, let's say, reproducing the shape of, is a gas that it's not reproducing the shape of its container. That's the key point. And so by tilting the orientation, you can actually control the relative strengths of the different orientation, because if you tilt, you would also change the dipolar interaction. Yeah. Yes.
Great. Okay, Derek has got a question. Derek Lee.
Hello? Oh, where am I? Yep. Hi, Derek Lee from Imperial. Thank you for a nice talk, Francesca. I was just wondering about the small droplet phase. Is it kind of small enough to make kind of interesting correlated physics, just like kind of bosonic version of quantum dots, where you might have interesting excitations? Have you done kind of spectroscopy on that?
So I'm not very familiar to quantum dot. Let's say to understand which type of excitation. So we have done a spectroscopy of let's say the excitation spectrum, and this roughly this excitation spectrum that I was showing before.
Yeah, I guess I was just wondering whether there were things in that excitation spectrum that you can't understand with mean field theory or mean field theory plus Li Huang-Yang corrections.
So, I mean, this is the spectrum of excitation, and the color code give you the normalized structure factor. So the dynamical response of the system to an excitation. And each of these blob that you see corresponded to a different, let's say, excitation mode, like in a laser, you could see. And so here,
yes.
This is before I show you the expectation spectrum of, let's say, what we call a linear supersolid. And here is it for the case of a 2D supersolid. And so 2D, so here is not yet supersolid, it's just an example of the type of mode you can have.
Yeah.
But I don't know how this really connect with, actually with your question of stuff.
Yeah, no, I guess I started off thinking about it because if you have isolated droplets and the mean field theory doesn't really work in that phase, maybe there is more interesting physics in there. I know you can put in these Li Huang-Yang corrections, but I think the basis of putting them in starts to fail when you have small dots. Because I think those were just calculated for homogeneous BEC, so.
Mm-hmm. Now, what we have done is, but I don't know if it's really connected to what you saw in 2000 slide. So actually what we did is going a little bit to the isolated droplet, as you mentioned. So, so let's say I kind of, what I can do, I go to these isolated droplets. You see each of these high density peak, and they don't speak to each other. Then if I simply let the system evolve, each of the droplet will let's say, accumulate a different phase.
Mm-hmm.
And so this is completely phase incoherent. And then what I can do, type of Josephson junction experiment, I can relink again my droplet.
Mm-hmm.
And so if I link again my droplet at the beginning, they're still phase incoherent. And one can ask if they find a way to dissipate this phase excitation and they would relock in phase completely or not.
Yes.
This is what we did, and we saw actually, but it's not completely clear, that the system can be described in terms of an array of Josephson junction with the tunneling constant,
yeah,
and you see that exactly that the system very quickly, really in the scale of 20 milliseconds, from completely incoherent phase, that they can spontaneously rephase down. Yeah. So there is a kind of. Yeah, so actually it's very, very fast. But of course, the problem is that there is no, so we don't have a microscopic understanding. So there is clearly, let's say, a dissipation with the reservoir. Maybe let's say where the phase excitation is going, let's say. We see that the phase excitation goes away very quickly. The system want to relock very quickly, but we actually don't know what
where the energy went.
Yeah. And what determined the scale?
Yeah. Oh, the time scale.
Yeah, and also where it went.
Yeah, that would be interesting. And presumably you can do this in 2D. You might be able to do this in 2D as well. That
Yes,
would be
sure.
interesting.
Yes.
Get funny.
Yeah, we just got the 2D 2 months ago, I guess.
Yeah.
Super solid, and now we need to understand how it behaves. I mean, there is a long list.
They give quite some vortices and things. That'll be fun. Yeah. Great. Thank you very much.
Okay. Thank you.
Good.
Okay.
Subia has a question. Subia, please ask your question.
Hi, I'm sorry, I missed the early part of your talk, so you may have covered this. Do you see more than one solid phase? I mean, depending on how you prepare the system, the solid breaks the translational symmetry in a different way.
So in different way.
Meaning, you have one pattern of positions and then they move a little bit, or they're reflected or something, or is the symmetry just essentially broken by the trap?
So we see indeed a number of I don't know if now I have I don't have the slide. So why you say the symmetry is broken by the trap?
Well, I mean, so it's not a translating invariant system to begin with, because it's a parabolic trap, I presume. But so you have these pictures where you're showing the one, say on the one of the two.
This one.
Yeah, for example, so you could imagine in the figure G there that you obtained another pattern which was reflected or something, or the atoms have moved a little bit depending on how you prepare the system.
Yeah. So first, so the point of the parabolic trap, I think it's a good point. But actually, what you could do is also completely uniform. That you could do the calculation, and you still have these phases.
On the calculation, I can believe that.
No, just to say that's not an effect related to the parabolic trap somehow. Okay. So because I could, for example, have a plane, a 2D plane. Okay. Let's say completely, and this would for a given atom number show the same. So very similar behavior.
Yeah, and but then, in the 2D plane, the center of mass will move around. So my question is, does the center of mass move a little bit depending on how you prepare the sample, or something like that? Yeah.
So the center of mass move. So, but this would connect not to the ground state, or you are interested on the ground state?
Well, what I'm really after is, in a true solid, there's a degeneracy, translational symmetry is broken, and so there's an infinite degeneracy of states. Now, of course, here you've broken translational symmetry by a trap. So I'm trying to get a sense of how close in energy are these degenerate solid states.
So I think, that. So you have a bunch of, let's say, metastable state, if this is the question, nearby the ground state. And these metastable states show different pattern.
Yes, that's roughly what I'm asking, yes.
Yeah, exactly, yes. And actually, yes, you have a bunch of these metastable states which are pretty close in energy, which kind of in some way, not directly, okay, I don't know, I don't have a good picture, but you could see, let's say how the mode nearby the roton. So if you see let's say the spectral density is very high here, you don't have really one mode, there are more mode, and if you try to look at at the shape, you have several levels very close in energy with a slightly different shape of the drop.
Okay, great.
Yes.
Okay,
but I don't have the figure for this, I'm sorry.
Okay, all right, wonderful. Thank you.
Great. John, did you have another question? Follow-up question? Or your hand is still up, that's why I'm asking. John Saunders, did you have a follow-up question?
Oh, no, sorry, that was a mistake, sorry.
Okay, very good. Okay, well, any other questions from the audience apart from John? All right, in that case.
I have a question. Sorry, my hand was up. I'm not sure if I did it wrong, but can I ask a question?
Go ahead, please, Ryan. Yeah. Sure.
So thanks, Francesca. This was a fantastic talk. I was really intrigued by this difference between where whether the density, the translation symmetry breaking of the density happened first as the system was cooled, or whether the phase symmetry was broken first as the system was cooled. And I was wondering if this is something that is tunable. Is this, do we understand why it happens the way it does? Can you imagine tuning some knob and making it happen in different ways?
So this is a very good question. Actually, it seems rather robust. So it's look like rather robust that the translation symmetry breaks first. And why it's really not, I don't think there is a clear understanding. So I was discussing, let's say, a lot with Prokofiev and colleague. I mean, and so it might be that there is, there is this in-between region between adding, let's say, the thermal population of the mode and the fully condensed system. There is this regime of quasi-condensation. And in this regime, you could occupy mode with a momentum which is comparable with the Roton momentum, let's say. And this type of population could indeed, let's say, foster the breaking of the translation symmetry before really you get full condensation. But I think this is not understood completely. Actually,
am I thinking about this right? That if I could just, obviously you can't do this in your experiment, but if I could just turn down the dipole magnitude, eventually I would get a superfluid before I broke the translation symmetry, right? If I had no dipole interaction, I would get a superfluid without translation symmetry breaking. So I guess, does that happen at a finite strength of the dipolar interaction, or does that happen for infinitesimal dipolar interactions, or do we just not know?
Okay, so if the dipole interaction is 0, you have always a uniform superfluid. And now, if I understand your question, is that if you now increase the dipolar interaction, is there any critical value for which? So yes, I would say. So the answer is different whether it's an experimentalist answer or a theorist, let's say, because let's say from the really the physical picture point of view. So you need to have a balance of different interaction into the system. So if your dipolar is, but there is no critical value of the dipolar interaction, let's say. You could always think to rescale in an infinite system and get somehow the dipole. But from the experimental point of view, you need to have a strong enough dipolar interaction such that you don't have to use the tuning of the contact interaction too much. Otherwise, you enter in a bunch of additional problems like three-body losses and things you really don't want to have. That's it.
Great, thank you.
Okay, well, I don't see any other questions. Let me try and ask a conceptual question here. In superfluids, we have the London acceleration equation, which tells us that if we have a gradient of the potential, the superflow starts to accelerate. But once we develop modulated order on top of that, what's the difference between the acceleration of the superfluid and the acceleration of a solid? I guess my question is, is it possible that what we're calling a super solid is actually just a solid? Is there a difference between the solid and the super solid? I mean, the London acceleration equation is what we expect for a superfluid, but we also expect it for a solid when it's rigid. It's just Newton's equation of motion. So
well, I think this is a very interesting, let's say, I think it's a super interesting question, the one you have touched. Yes, I think it's really the point where we are now to try to understand, because I mean, you can see, so for example, you can study the moment of inertia, and you could know, so there is the rigid, so the rigid moment of inertia.
Yes.
And we already have, I mean, this is things going on now in the lab, and we see clear deviation from the rigid case, so the solid case. But now the problem is this enough to say something about superfluidity? Yes. And I think it's not enough, and it's much more complex, the answer. So I think that's really the key, the core point where we are now that we need to understand. I mean, it's incredible that in cold atom experiment, I learned, but it was a surprise for me, although I'm working on this field since 20 years, that in reality, don't think about supersolid, just a BEC of atom. Actually, who has really demonstrated superfluidity? So actually, it's almost given a little bit for granted in the picture of Nozier, no? That say, okay, phase coherent interacting systems are superfluid. But really proof of superfluidity, there is just one work in, I think in Gretchen Chamberlain and Bill Phillips regarding a persistent current in a ring. And then there is some work on the quantized vortices. But actually the superfluid, and now you have a system that challenge you, because I mean, what are the superfluid properties? And this is really where we have to go, well, I think.
Yeah, of course, in liquids, there's no question about superfluidity. You have fountain effect and everything else, but you're talking about cold atoms when you're saying this.
Exactly.
Yeah, very good. Well, if there are no further questions, I may have missed some because I can't see everything here. You're welcome to unmute if you've got a question. Otherwise, let us all give Francesca a big hand. Thank you so much for this very interesting and stimulating talk this afternoon. Thank you very much.
Thank you to you. Thank you.
Thank you for coming. Okay, we're now going to take a half-hour break before we resume with Claudio Shimon in half an hour. Okay, and I'm going to stop the recording.
Thank you very much. Thank you for the invitation.
Welcome, Francesca. Thank you so much for coming.